Hi everyone, myself Bidyulata Sahoo, working as an assistant professor in the Department of CSC, Artificial Intelligence and Machine Learning at Institute of Aeronautical Engineering, Hyderabad. This is my second video lecture on the course Applied Artificial Intelligence, and today I'm going to discuss about the topic local search in continuous spaces. These are the topics to be discussed. First, I will discuss what is the meaning of beyond classical search and what are the classical search methods already we have used, what are the challenges of the classical search methods, then the discrete environment and the continuous environment, what is the difference between these two, then what is the meaning of local search and why we are going for local search techniques, and what is the meaning of continuous spaces, solving optimization problems in continuous spaces. Then we'll discuss one of the technique which is called as the gradient method of the objective function. What is the purpose of the gradient in optimization, and different techniques for local search in continuous spaces. And we'll discuss the difference or the comparison between the gradient based and non-gradient based search methods in common spaces or continuous spaces, and few applications as well as examples. Okay, so before going to start about this local search in continuous space, we should know what is the classical search method. Already we know in artificial intelligence, the classical search method, which is also called as like state space search, means where the state space is fixed and all the informations about the state space is known to the agent in advance, and agent can move, agent can explore based upon the existing information. Then it is called as a classical search method. Normally for classical search methods, we used to use the algorithms like breadth first search or depth first search or A-star algorithm or uniform cost search. So those kind of search technique, either like uniform informed search or uninformed search techniques can be used. So both informed and uninformed search techniques comes under classical search methods. But beyond the classical search means if the state space is too large or a number of iterations are required to explore the path or to find out the optimized result, then we can go for beyond classical search. That beyond classical search is nothing but our local search, where the information about the state space or the environment will not be known to the agent in advance. So while exploring the environment, agent has to understand the information, agent has to perceive the information from the environment, as well as it has to adapt to the situation, and it has to find the optimal solution. So let me discuss what is the meaning of beyond classical search. So beyond classical search refers to explore the advanced problem solving techniques in artificial intelligence that address the scenarios where the classical search methods are inefficient. Just now I told what is the meaning of classical search methods, like informed search, our informed or uninformed search, right? So both search techniques are called as classical search methods. When classical search method cannot find the solution, then we'll go for beyond classical search. So classical search methods already we know, we assume that it is idealized for the environment, often characterized as it is observable, deterministic, static, with well-defined problem states and clear solution. So whenever we used to use or we want to find the solution using classical search methods, whether it is using informed method or uninformed method, so all the classical search methods are observable. That means agent can understand, the agent will have the complete information about the environment, completely observable. Whole information would be there to the agent in advance. And deterministic. Deterministic means what? The output of every action can be predictable. That is called as deterministic. And the state space means the environment is fixed. It is not going to be changed, with well-defined problem states and clear solutions. With well-defined problem statements means the protocols also it would be known to the agent. The steps, how to follow the path, how to find out the solution, everything will be known to the agent with clear sequence of steps with solutions. So those type of environment or methods comes under classical search methods. If you take the example of the chessboard, the complete information how to play chess game, we know everybody the rules and regulations, and if we move forward what will happen, or if you move diagonally, or if you move back then what will happen, all possible combination of movements, everything will be known to us, or everything will be known to the agent. If the computer is playing that game, then it is considered as an agent. And the environment means the chessboard, it is fixed and the number of squares are not going to be changed. That is why it is called as static environment or static state space search with well-defined problem states and clear solution. But if the state space is too large, which is not beyond our imagination, or the environment is dynamic, or the environment is not observable, which is partially observable, then we can go for this beyond classical search, which is called as online search. So these are the challenges of the classical search methods, what I have discussed just now, like exponential growth of search space. If the state space will increase more than the required number of steps, or if it requires more number of iterations, then in that case we cannot use classical search method. And memory limitation is there. To solve memory limitation means it can be used, the memory can be used for a fixed number of steps, like the stack and queues normally we used to use for the exploration of breadth first search algorithm or depth first search algorithm. Whereas if you want to search for the online search algorithm, then in that case it is not possible. So that is why limited memory is there, limited memory configuration would be there for classical search methods, and the environment would be fixed, which is called as the static, and it cannot be used for the dynamic natures, and uncertainty and incomplete information. That means if uncertain information is there or incomplete information about the state space is there, then in that case classical search methods will not work out. Even it struggles in the domain with infinite or continuous states. Infinite means number of possible number of iterations, as well as the state space. If it is continuous in nature, then in that case also classical method will not work out. So that is why these are the challenges of the classical search methods. Now, in contrast, if we talk about this beyond classical search, which is our local search technique, it deals with more complex and realistic situation. Like in real life, we can use this online search or local search. So these are few properties of the online search which we cannot do using our classical search method in artificial intelligence. So the beyond classical search methods can work for stochastic environments. Stochastic environments means where the outcome is probable or probabilistic outcomes we are expecting. In that case, this beyond classical search will work out. Even this beyond classical search can be used for partially observable environments. That means when all the informations about the state space or the environment is not known, at least partially known, 50% is known to the environment, in that case also beyond classical search can be used. How 50%? If, for example, if we take like a self-driving car, when it drives on the street, then it can observe, the sensor can observe up to certain distance, maybe 50 meter or 100 meter, but beyond that it cannot predict where the obstacle would be. So that type of environment is called as partially observable environment, where the agent, the self-driving car itself has to explore during its exploration. And this beyond classical search technique can also be used in the dynamic environment, means changing environment, means it is not fixed like the chessboard or tic-tac-toe game, or it is not fixed like Ludo game. Dynamic environment means suppose we are sending one drone from one place to another place to deliver the packets. In that case also what will happen, drone has to explore the path, because all the informations about the environment may not be known to the drone, which is called as the agent here. So while exploring the path, any uncertain situation may happen, like wind pressure may come, or very drastic situation may happen, or many pressure, or pressure may come, or may any device of the drone may fail. So in that situation, or the environment may be foggy, or it may be rainy. So depending upon all this situation, it has to adapt and it has to explore the environment. So that type of situation is called as dynamic environment. So beyond classical search techniques is a work code for dynamic environments. Even it is used for large and continuous spaces, where the large and continuous spaces I will explain in this video, do not worry, like where we can assign some values which are in continuous in nature. Like if we take the example of the AC values, if it is like 16 to 30 degree, then we can assign 16.8, 16.9, 17.10, or 17.9 or 18.9. So like this, all the values ranges between 16 and 30 can be continuous in nature. And multi-agent system where more than one agent, they work out to solve a complex problem. So all these are the characteristics of the beyond classical search, which is not possible in our classical search method. So these scenarios require advanced techniques like local search, optimization algorithms, probabilistic reasoning, planning under uncertainty, and heuristic methods to find the solutions effectively. Now, let me discuss what is the meaning of discrete environment and continuous environment, because the topic is our local search in continuous space. To understand clearly, we should know the clear distinction between what is discrete environment and what is continuous environment. So discrete environment, actually, if there are a limited number of distinct, clearly defined states of the environment, that environment is called as discrete. For example, a game of chess or checkers where there are a set of number of moves. Now the picture which is given on the screen is a chessboard, and already we know that in the while playing the chess game, how many possible number of movements are there, and this number, the protocol for playing the chess game, everybody knows. So that is called as the clearly defined states of the environment. So discrete environment where which consists of distinct number of movements, distinct number of states, and the state space. Here the complete chessboard is called as the state space where the game will be played. So that is, this type of environment is called as discrete environment. So compared to the discrete environment, another environment is there which is called as continuous environment. So continuous environment means what? Continuously the agent will be perceiving the information, and based upon the information, current information, the agent will start behaving. So continuous, here in this picture you can see this is a picture of the self-driving car, or you can take the example of normal car also. So whenever the car moves on the street, it can observe up to a certain distance, but it cannot observe in front of this car is there. So this car can sense that how much distance it needs to maintain from this car, and if this car changes the lane, then how much distance it needs to maintain from this car. So how it can sense? Because of the sensors which is present in the car. So continuously the sensor of the self-driving car senses or perceives the information from the local space. Based on that, it act on the environment. So that is why it is given that continuously signals constantly coming into the sensors, actions continually changing. So most of the real world environments are continuous in nature, whether you are taking up the example of the self-driving car, or whether you are taking the example of your cycle, or whether you are taking the example of the drone. All the equipments, all the devices or the vehicles, they will work in a continuous environment where they have to, or the sensor has to receive the information, and based upon the current sensor's information, it has to act upon the environment. Now that is why this example is given, taxi driving. So there could be a route from to anywhere else, or simply driving a car also. So beyond certain limit, the car cannot understand where the object is, or where the obstacle is, where the human is standing. It cannot observe up to certain distance, either this left side or to the right side, or front or back, little bit back through the mirrors it can observe, not beyond its observation. So that is why this type of space is called as dynamically changing space or partially observable environment. It is not a discrete space, it is a continuous space. continuously. It's not like every time the car will move forward and the car will move backward or car will take left turn. Continuously it may change to any direction, it can change the lane also. So the environment is continuously changing, and you can understand environment is continuously changing. I'm saying the like depending, that also depends upon the traffic. If the traffic is very low, in that case the car can move very fast. If the traffic is very crowded, then it has to stop, and it has to move very slow, or it has to maintain the distance from the front vehicle. So that is why it is called as the continuous environment or partially observable environment. I hope you might have cleared what is the difference between the discrete environment and continuous environment. Now let me discuss what is the meaning of local search. So this is the main topic of this particular video. Local search is a type of optimization technique which is used in artificial intelligence to find the best solution of a problem or to a problem. Now we suppose we will solve one mathematical problem. So same problem we can find the solution in different ways, but the solution which gives the same problem can be solved in 10 ways or 5 ways, but which solution is the optimal one? How we can recognize which gives the correct answer with a limited number of time or with a limited number of steps? That is called as the optimal solution. So local search is a type of optimization technique which is used in artificial intelligence to find out the best solution among all possible solutions. So instead of examining all possible solutions, it begins with an initial guess and iteratively improves the solution by exploring its neighboring solution. So the process continues until an optimal or satisfactory solution is found. So local search algorithm, so where the path cost does not matter here. Now if you take, now already we know the classical search techniques, and we used to find out the time complexity and the space complexity for breadth first search and depth first search, means how many number of steps it requires to reach from initial state to the goal state. So that is why we need, and how much space it consumes inside the memory. So which is called as the space complexity and time complexity. So both the things are not important here. As it is a local search technique beyond classical search, so path cost does not matter. So what it matters, whether it is finding the optimal solution or not. We know that there will be many possible solutions, but out of that, which one is the best solution? You take the example of the GPS map. So whenever we start from our home to the destination, we used to open the map in our like using Google Map, and we can find out, and the Google Map automatically it will show you which one is the optimal solution or optimal path from your location to the destination based upon by considering all the factors over the street, whether it is like based upon the environmental condition, based upon the traffic condition. So all the conditions it takes care and find out the optimal path from starting location to the ending location. So that matters a lot in a dynamic environment or a local search technique. Now why this continuous spaces we need to consider? So in some problem we know that the variables can take any value within a range. It may be 0.1. Suppose I'll say like the value ranges between for a particular device, or for a fan speed we can take the value like 1 to 5. So I can set it 2, I can set it 3, I can set to 4. So these are fixed values. We cannot change, we cannot fix like 1.5. I cannot keep the regulator between 1 and 2. I cannot keep the regulator between 2 and 3. These are fixed. So that is why this is called as the fixed number of values. But this does not come under your continuous space. Continuous space means where the value ranges between two particular values. Now you take the example just now I have given the AC temperature. If you want to fix, I want to fix between 16 to 30 degree, then we can make it 16.5, we can make it 17.9 or something. So those values are called as the continuous spaces, which the number where we can represent using the real numbers, so leading to a continuous space. But this is different from the discrete space where the value have a fixed set of values, often integers or the categorical option like 0, 1, 2 and 3. So a local search algorithm completes its task by traversing on a single current node rather than the multiple paths and following the neighbors of that node generally. So how local search techniques explore the path? As I told, local search is used to find out the optimal solution. How it explore? Will it explore all possible paths at a time? No, it is not like our classical search. It will follow a single path by observing the neighboring solutions or solution of the neighboring state. If the solution of the neighboring state is better than the previous state, then the neighboring state solution will be considered as the current state. So like this, it will try to explore the complete path until the optimized result is not found. Here you can take the example of the hill climbing or the simulated annealing. We know, and these type of algorithms are used to solve the local search technique in continuous spaces. It can handle the continuous states and action space as they have infinite branching factors. Now, let me discuss what are the techniques are there to solve the optimization or the continuous spaces. So solving optimization problem in continuous spaces, there are two key approaches. One is the discretization of continuous space. Means how many ways we can solve the continuous space problem to find out the optimization result. So one way is the discretization of the continuous space. Another one is the gradient based optimization. Now what is the meaning of discretization of continuous space? If the space is continuous like this, then for a particular moment of time, so nearer to this place, whatever the number of points are there, like here, we have to explore first this number of points, and each location is considered as the candidate point for the exploration. So here what is given, instead of allowing the variables to take any value, the continuous space is converted into discrete steps. Suppose we want to explore only this much path, then I will explore this path. So first let us explore this path. So this path, and we'll take one solution, a random solution from here, and neighboring to that solution will up to this range will divide into a number of discrete points, and these discrete points are considered as the candidate points for its exploration. So candidate points for the exploration means whenever we are assigning any particular solution, initially that solution gets compared with the neighboring solution, whether it is good or bad, then it compares to the next solution. Like this, it explores only up to certain distance. Once it is over, then it will move to another distance, then it will move to another distance, then it will move to another distance, and all the distances discretized, like it will be divided into a number of discrete points, and each point will be explored to find out the optimal solution. So that concept is called as discretization of the continuous space. And another method is there, gradient based optimization. Normally the gradient based optimization method, it is used for smooth surface, where gradient means the slope, where we can find out the slope of the space. That is why it is called as gradient based optimization. We can find the optimized result using the slope based method, that is called as the gradient based method. So that gradient based method, maybe it is gradient descent or gradient ascent. So slope can be in the negative direction or slope can be in the positive direction, and it is similar method use the gradient slope of the function to move forward towards a maximum or minimum. So normally gradient descent method, it is used when the surface is completely smooth. Smooth means what? Like this particular surface is very smooth, so we can find out the slope here, then after for this point, then we can find the slope here at this point, so then we can find the slope here at this point. So based upon this slope, either in the gradient ascending order or descending order, which is called as gradient descent. Descent means down, towards negative side, gradient ascent means towards upside. Okay, so that is another way we can use it to find out the optimization result. So here one important point, just I want to tell you, the gradient of the objective function is a vector of what is the vector here? The nabla of f. This symbol we used to pronounce as nabla of the function f, that gives the magnitude and direction of the steepest slope. So how to find out the gradient of the objective function? Now you might be thinking, oh, this is another new term. So what is the meaning of the objective function? So whenever we used to calculate the gradient at a particular point, for example for this point, so we have to define one of the objective functions. So this is one kind of function, like you might have known, y is equal to mx plus c. This is the linear equation, we can say. So m is the slope and c is the y-intercept, right? So this type of equations normally we used to use for linear regression, or where the curve is linear in nature. So here the objective function, what it says, the objective function normally we used to use in the local space to understand whether the solution is a good solution or it is a bad solution based upon the objective function. It's not like just I'm giving one example, y is equal to mx plus c. The objective function differs from the context to another context. So objective function normally what it says, it defines whether our solution is a good solution or bad solution. So if it is a good solution, it is well and good, and if it is a bad solution, it will try to improve its solution for the next time. So here the gradient always, the slope always, it will be calculated for the objective function using this vector, using this function nabla of f. So which gives the magnitude and the direction of the steepest slope, whether it is gradient descent or gradient ascent. So the gradient of an objective function refers to a vector of partial derivative that indicates the rate and the direction of the steepest ascent or descent of the function at a particular point or at a given point. It is a mathematical tool. The objective function, it is a mathematical formula, or it is a mathematical tool which is used in the optimization to guide the search process for optimal solution. That means we can find out the maximum or minimum value for the function. So here what I have given the example here, suppose the objective function is like this, y is equal to mx plus c, then the partial derivative of this objective function will be calculated, which is nothing but the nabla of f. So it helps to identify how much small changes in the input variable affect the objective function. So that means what, if we change the value of x, how much there is a change in the value of y. So whether it is directly proportional or indirectly proportional, that we will get to know. So that is what the small change in the solution, we can find out the small change in the solution from one point to another point. It is called as the learning rate, and the value which assigns the change in the value, that is called as the step size. Anyways, I'll discuss again here. So mathematically, how we can define the continuous space, this is what the solution here, this is what the formula we have to use, or the expressions we have to use. So suppose given a continuous space S, where each state is defined by n variables. So this is a continuous space. As I told that a particular space can be defined with a n number of states or variables. So these are the variables x1, x2 and xn, where each xi, I stands for 1, 2, 3 up to n, belongs to the set of real numbers, R means the space is continuous rather than the discrete. So mathematically we can represent like this. Here S is the continuous space, that is equal to x1, x2, x3 up to xn, which are nothing but the n variable or n states such that xi belongs to R. I stands for 1, 2, 3 and all the numbers belongs to the real numbers, and this is the objective function for the continuous space f of x1. Now for this discrete number of steps, we have to find out function of that one. So f of x1, x2, xn, how we can find out? If we define the objective function f of x1, x2, xn, then we have to find out the derivative to find out the gradient. So the gradient is a vector of partial derivatives of the objective function. This is what the gradient says. How we can find out the gradient? This is the formula nabla of f. Already we have defined f is equal to x1, x2, xn. So here nabla of f is nothing but the gradient or gradient vector, and we can find out using the partial derivative of each number of steps. So here partial derivative of this we can read as partial derivative of f with respect to partial derivative of x1, partial derivative of f with respect to x2. For each variable we have to find out the partial derivative, and here each component, the partial derivative, represents how the function fx changes with respect to the variable xi, keeping other variable constant. Now whenever we are calculating the partial derivative of one variable, partial derivative of f with respect to x1, we have to keep other variables as constant, and then we will go for next one, keeping other variables constant, then we'll go for the next one, keeping other variables constant. So like this we'll move on to find out the optimal solution. So that is the concept of the gradient method in continuous space. Now what is the meaning of direction of the steepest ascent and direction of the steepest descent? Simple meaning: positive direction and negative direction. So direction of the steepest ascent means the gradient point in the direction where the function increases the fastest. Right? Increases the fastest means the gradient increases the fastest. If it moves in the downward direction, that is called as gradient descent, gradient steepest descent. So here we are calculating nabla of f, positive nabla of f, but here we are calculating negative nabla of f. So for each value of x. So that is the difference between direction of steepest ascent, direction of steepest descent. Now let us consider one example to understand this gradient method in optimization technique or in local search. So let us suppose this is the objective function, which is called as the simple function fxy. Here we are considering two variables, fxy is equal to x square plus y square. So in mathematically we can represent like this: x caret 2 plus y caret 2. So first, how to compute the gradient? Gradient symbol is nabla of f of xy. So just you find out of nabla of xy. So as I have told how to find out the gradient. This is the formula. The partial derivative of each variable we need to consider. The same thing here. What is the partial derivative of x square? That is partial derivative of f with respect to partial derivative of x. Same thing for y square, partial derivative of f with respect to partial derivative of y. So x square means here f is equal to x square first term. So x square means it would be 2x, and y square means it would be 2y. Now we have to select one particular. This is the generic formula or general for the gradient method we calculated. Now we'll substitute the value of x and y. Let us suppose at the point x is equal to 1, 1. What would be the gradient value? Gradient value would be 2 into 1 and 2 into 1. We will get 2 and 2. So these vector points in the direction where xy increases the fastest. So for this is for the gradient ascent. So for gradient descent, we move in the opposite direction. So if we move in the opposite direction from a particular point, suppose this point or this point, the new point, how we can calculate? The original point xy minus, this is called as alpha, which is called as the learning rate whole into nabla of fxy. What is nabla of fxy? Already we have calculated this one. Now you will substitute the value of x and y, you will get the value of new point. So like this, the solution, when the local search uses the gradient method, it tries to find out or tries to explore the neighboring state by following these formulas. Okay, so for this is for the original point and this is for the new point, and while exploring the new point, here it is considering another parameter that is called as alpha. Here alpha is called as the learning rate and it controls the step size. Learning rate means how much cost whether it is increasing from the current point to the next neighboring point or whether it is decreasing from current point. Suppose this is my current point and this is the next solution at the current point and solution at the neighboring state. So learning rate, what is the learning rate? How fast it is quickly trying to find out the optimal solution whenever it improves the step by step. So from here to here, or from here to here, and from here to here. So how much steps are, what is the value what is the maximum value it is taking to change? So the magnitude of the value is called as the step size, but the ratio or the proportion it is called as the learning rate. So learning rate, it may be very small. Normally we used to use 0 to 0.5 while solving the algorithms. Now let me discuss different techniques for the local search in continuous spaces. There are 4-5 techniques are there. This is the first technique, which is called as hill climbing. One more technique is there, This is your simulated annealing and the evolutionary or genetic algorithm, as well as gradient descent. Just now I told what is the meaning of gradient descent. Apart from that, these are other techniques also which is used in the local search in continuous spaces. So hill climbing, as the name it implies, the agent will climb the hill. It's not like we will climb the hill. This is one of the method or the algorithm which is used to solve the problem in continuous spaces. So hill climbing algorithm says that it starts with a random solution at any point of time, then moves to a better neighboring solution. Okay, let us suppose this is the better solution, and stop when no better neighbors are found. That means while exploring the path, it may find the better solution compared to the previous one. It may find the better solution here compared to the previous one. So like this, it moves on, and when it stops, when there is no other better solution is found compared to the previous solution. Now after this, if you see, this would be the better solution because this is the peak point of the hill. After that, the agent has to come down. So it may not get the better solution here. So hill climbing problem says that it starts with a random solution from any point of time and moves to a better neighboring solution and stops when there is no better neighbors are found, and it works well for the problems with smooth landscape and a single global optimum. Smooth landscape means where it can for every the agent can move very smoothly from one place to another place during exploration, and a single global optimum. That means this is one of the diagram. Or else, if so, for example, the space is like this, and like this. How many optimal position is there? One position. This is the optimal position of this hill, or the highest position. So to solve this type of problem, the hill climbing method can be used. That is called as the global optima. But still some problem is there. What are the problems or the limitations of the hill climbing? It can get stuck at the local maxima. Local maxima means, suppose we will start with the random solution here and it will explore the neighboring points. When it reaches this peak point, at this point, the agent may not find no better solution further. So it stops its process. But there may be some other global maxima. So that is the main problem here in hill climbing. Once it finds the local maxima, it does not explore further. Another problem is the plateau. Plateau means what? Suppose the space is like this. Then in that case, this flat region is called as plateau. So it starts with the random solution and moves forward like this. Once it reaches here at this point, it may not move further. Even if it moves also, all the solution for these locations will be same because that is a flat region. So that is another problem which we face in the concept of hill climbing. So that problem is called as plateau, which is called as the flat region. Another one is the ridges. Ridges means what? Suppose we'll take the example, the surface is like this. Sorry. Let me draw once again. Like this. Okay. So what happens here? This is called as the ridges, steep but narrow paths. Means if you starts at any particular solution, at this point the value is same. Even it moves down, if you see, all the values are same over here. So in that case, that is called as the ridges. Steep but narrow paths are there. So all these problems cannot be solved using the hill climbing. Though hill climbing method is used to solve the problem in continuous spaces, but few limitations are there because it gets stuck at the local maxima. That is the main concept of hill climbing. This pictorially or the graphically, we can represent the hill climbing problem like this. This is the graph between various states of the algorithm and the objective function. So x-axis represents different states of the hill climbing problem and y-axis represents the objective function. So this flat portion is called as the shoulder or the plateau region where the agent may not move further once it reaches here. This is one of the problem we used to face in hill climbing algorithm. This point is called as the global maximum. If the surface is completely plain, then it can reach, definitely it will reach the global maximum, which is called as the optimal solution, we can say. While traversing, sometimes it may face like this. Suppose the current situation is the agent is present over here. So this position is called as the local maxima because Local maximum means definitely one global maximum would be there. This is called as global maxima. This is called as local maxima. And here again the flat region is there, that is called as local maxima. Again we can say that is called plateau region. So these are the problems or the different states we used to find while exploring using the hill climbing algorithm. Now another algorithm is there which is used in the local search, that is called as simulated annealing. So simulated annealing, normally it is used in the process of annealing process in the metallurgy. Like annealing process means it allows the metal to be melted with a high temperature, and immediately it cools down to maintain its crystalline state. So that type of process is called as annealing process, which is used in the process of metallurgy. The same concept is also used in the local search in continuous space. Sometimes it allows to move to the worst solution to avoid getting stuck in local maxima. As I told in our hill climbing algorithm, sometimes like if the space is like this, after reaching here the agent may stop. Even though there is a global maxima, it stops at the local maxima. This is our global maxima, right? So that problem, to overcome that problem, this simulated annealing is used, which allows the moves to worst solution to avoid getting stuck in the local maxima. How it allows, I will tell you here. So gradually it reduces the likelihood of bad moves over time. So effective for the problems with the many local optima, or when the search space is highly irregular, such as optimization in engineering design. So where we can use this type of simulated annealing algorithm? If the surface is too rough, it's not smooth. Now you can see this diagram here. This diagram is not smooth like this type of diagram. This is little bit rough or very rough, we can say. Many jumps or many humps are there, like it comes down, then immediately goes up, then comes down, then immediately goes up. Very sharp edges are there, and the surface is not completely smooth. So that is why we can go for the simulated annealing. So, and how it moves, it says that it allows the moves to the worst solution. That means the same like our hill climbing starts with the random solution and moves in the forward direction once it reaches the local maxima here, because this is the first local maxima. The local maxima means definitely there will be global maxima. So it does not stop here. What it does, it moves back to the original condition. Again it takes a jump to another location. It may be the global maxima. Suppose this is not the global maxima, again it is a local maxima. What it does, again it moves back to the previous location, then it jumps. So like this, it tries to explore and tries to find out the best solution among all possible solutions. That is why this process is called as simulated annealing. And it moves to the worst condition, means it moves back to, which is called as the probability of -1 also. Moves back, again it takes another path and tries to find out the global optimum solution or the optimization solution. Now the third type of technique or the algorithm is evolutionary or the genetic algorithm. As the name it implies, it is related to the genetics, so it mimics like a natural selection. So it starts with a population of the solutions, combines good solutions, and introduces small problem changes. So small random changes by applying the operators like selection, mutation, and crossover. Whenever I'll come to the genetic algorithm, definitely I'll discuss all these points, and evolves better solution over time and suitable for highly nonlinear or non-differentiable problem. That means where the objective function is not differentiable or the space is not linear, like where we can use the hill climbing algorithm. In that situation, we can go for these genetic algorithms, like the optimizing the hyperparameter in machine learning and or aerodynamics design. And the fourth type, which I have already discussed, this is the primary requirement. This technique is normally we used to use to find out the optimal solution in the continuous spaces or in the local search. It utilizes the gradient or the slope of the function to move iteratively towards a local minimum. So variants like the stochastic gradient descent, which can find the probable answers, which introduces the randomness to improve the scalability. And it is suitable for convex optimization problems, machine learning model training, or when gradients are easily computable. So normally the gradient descent method is also used whenever the space is linear and where the objective function is differentiable. These are the small tricks we need to remember where we can apply this gradient method. Now let me discuss the comparison between the gradient based method and non-gradient based method. So as the name it implies, gradient method and non-gradient method, search method in continuous space. So here the gradients of the objective function is used to guide the search towards the local minima or maxima. Whereas here we use other heuristic function or heuristic values. Heuristic value means one non-gradient based method where we can use the heuristic value, the approximate value from the current point to the destination point. That is called as the heuristic value for random exploration or population based strategies without relying on the gradient information, like our BFS or DFS. Here the example you can take like gradient descent or stochastic gradient descent and trust region method. Here you can take the example the simulated annealing or genetic algorithm where the gradient cannot be, or the objective function will not be differentiable. Now you based upon the suitability, both the gradient and non-gradient method, how it works. So based upon the suitability, it struggles with the noisy or the non-smooth function, because as it is a gradient based method, the objective function should be differentiable. If the objective function is noisy, means it is not differentiable, or it is a non-smooth function, then it will not be suitable. But in this case it is effective for noisy or non-smooth function, because we are not calculating any partial derivative of the objective function. Here directly we are using the heuristic value for exploration. And where it is used, what are the applications, like it is used in machine learning optimization, physics simulations with smooth potential landscape, whereas this non-gradient methods are used in engineering design, hyperparameter training and optimization problem with multiple optima or non-differentiable functions. Based upon the computational requirement, how the gradient based method and non-gradient based method works. The gradient, it requires the gradient computation. The gradient based method, it requires the gradient computation which may involve analytical derivation or numerical approximation, because we are calculating the partial derivative. But here it does not require any kind of gradient computation, making them suitable for non-differentiable function or noisy function. And here the speed is generally very fast when gradients are available and smooth landscape exists. But here the speed is typically slower due to the reliance on exploration rather than directional information. Now these are various applications of the local search in continuous spaces, means where it can be used. This type of algorithms can be used in robotics and like in machine learning, even in engineering also. Robotics, why it is, because all the three applications whatever I have mentioned here, all works in the dynamic environment or partially observable environment. That is why robotics is one of the best example, because robot has to explore the partial observable environment to work and to find out the goal state. So finding the best path for the robot, that is first application. Second application in machine learning to optimize the model parameters, and the third application, it is also used in engineering for designing the structure of the systems with optimal performance. This is one of the example we'll understand by applying different techniques of the local search technique, so that our clarity will be clear. Let us suppose we'll imagine you are climbing a hill in a foggy environment, and the hill represents the objective function. You cannot see far ahead, so you feel the slope of your feet. So if you apply in this situation hill climbing algorithm, so what will happen? You keep walking uphill and until you cannot go higher. Up to which distance you can move on the hill? Up to the peak point of the hill. After that we cannot move further. So that is the concept of hill climbing. The same thing, if we apply for simulated annealing, what will happen? Occasionally walk downhill to explore other path, then go to uphill. That means what? If we apply the simulated annealing process, we may start with this. Okay, we'll come back, or else we'll take another path so that we can reach. If we are not finding the optimal path, we'll come down Okay, again we'll find out another path. So like this we will change, and again we will change up and down, and we may come back to the drastic situation which is called as the worst case possibility, where probability will be -1. Then we can find out the best possible solution. That concept is called a simulated annealing. And genetic algorithm, if we apply, imagine multiple climbers. Suppose you are not alone, you are not climbing the hill, along with your friends are there. So imagine multiple climbers trying different paths, sharing their best routes and trying the slight variation. Suppose 10 members are climbing the hill, 10 members, they will share their informations with each other, who has reached first to the peak of the mountain. So based on that, the final answer would be calculated. So that is called as sharing of the information between multiple agents. So that concept is called as genetic algorithm. So these are the oral concept of these particular algorithms. Using the example we can understand. Now one question comes in our mind, right? Does the local search algorithm work for the pure optimized problem? Definitely yes. The local search algorithm works for the pure optimized problem. So what is the meaning of pure optimization problem here? It is one where all the nodes can give the solution. But the agent is to find out the best solution out of all the according to the objective function. Unfortunately, the pure optimization problem fails to find high quality solution to reach the goal state from the current state. As I have already discussed, the local search techniques in continuous space does not matter how much cost is required or how many number of steps are required. Whether reaching the goal state or not, that is the target, that is the goal of the local search in continuous space. And why it can be used for the pure optimization problem? Optimization problem means where we can find the best solution among all possible solutions. As it is applicable to find out the best solution among all possible solutions according to the object function, definitely it can work out for pure optimization problem. But the problem is it may not give the high quality solution like our normal search techniques. That is the biggest problem of the local search, but approximately it will give you the solution. So this is all about for this particular video lecture. I hope you might have understood and enjoyed. So for the preparation of this video, I have referred this Russell and Peter Novick book for artificial intelligence, even Soros Kosik for artificial intelligence. So I hope you might have enjoyed. So thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.